Self-driving technology has made LIDAR a hot topic, but there are a lot of myths. So here's one resource for how LIDAR works and the pros and cons of each of the technologies for self-driving: LIDAR, radar, cameras and sonar. Hopefully, saving the need for repetition in upcoming videos about self-driving and what's required and who's up to what point in getting to fully automated self-driving. This is the One Finite Planet EV video on the sensors for self-driving, which have far wider implications and play an increasing role in how AI and robots form their world view, and are revolutionising areas as diverse as from how mobile phones process images through to evaluating tree canopy coverage and health of the environment. There are some other sensors to be covered in other videos, but this relates to these sensors that operate at a distance. LIDAR and radar are so similar that in fact the best description of LIDAR is to call it microwave radar. Doesn't help if uncertain about what radar is, and perhaps the best way to understand how all three of LIDAR, radar and sonar work is to start with sonar, and start by considering how a blind person navigates by making clicks and hearing the echoes. I'll try and link a video below, but the general principle is a person can point in a certain direction, make a click, hear when the echo comes back, and work out how far away the closest thing is. Turn their head, make a click in a different direction, and they can build up a bit of a picture, quite low resolution, of the world around them and what objects are close. Of course, sonar is using vibrations or sound. Do we call it sound when the vibrations are only in the range we hear, or do we call all vibrations sound? I think that varies from person to person and the situation, but you get the idea. LIDAR, radar and cameras all use photons or the electromagnetic radiation. Do we call all electromagnetic radiation light, or only the frequencies that we can actually see? Once again, that varies, but the concept is the same. It's all the same thing, with a key difference being the frequency of the photons or light that is in use. The sonar sensors in cars work at a frequency the humans can't hear, so it doesn't disturb us. They work at around 40 kilohertz, which is around double the frequency we can actually hear. It's still, interestingly enough, within the frequency dogs can hear, but just like the blind person's clicks aren't that annoying to us humans, the sonar is actually only making little clicks, and most of the time making no sound at all, so it's not that annoying to dogs either. The radar used in cars is typically millimetre wave radar, which describes everything from 30 to 300 gigahertz, but in cars it's typically in the 76 to 81 gigahertz range, which has an approximate wavelength of around about 4 millimetres. LIDAR typically uses photons in the near-infrared range. In fact, almost all cars use either 905 nanometer, which are in the 200 GHz to 1000 GHz near-infrared range, or 1550 nanometer. Cameras use photons in the visible spectrum, which is round about 400 to 700 nanometer wavelength, or 400,000 GHz to 790,000 GHz in frequency. As you can see, there's a bit of a gap, but not a huge gap, between the lowest frequency of light we can see and that higher frequency of LIDAR that's in use. This means that that higher frequency light is just below the frequency of visible light, which does restrict it because it can still be picked up by human eyes. Not seen, but it can still damage the retina or damage the eyes if a strong beam hits human eyes. The slightly lower frequency has lower resolution because of being lower frequency, but can be sent at a higher level because it won't be picked up by human eyes. As frequency decreases, wavelength increases and resolution decreases. So once you get down to the level of radar, you end up with those blurry pictures, even with high resolution radars, images such as those taken by the US Defense Department of UFOs, or UAPs as they call them, which end up being quite blurry despite the equipment being very high level. The other impact of changing frequency is that the photons can move through different material, enabling going through fog and even going through, once you get low enough, going through walls. But at the same time, this also can make things invisible and changes even what can be used as the housing or over the front of the higher frequency LIDAR, you end up with a purplish, bluish looking, almost glass-like covering, although optical glass, as used by a windscreen, tends to be quite opaque to even this frequency. So LIDARs can't normally be mounted inside the vehicle and look through the windscreen. The higher 905 nanometer frequency for LIDAR is particularly bad at going through most glass, and you end up with covers that are polycarbonate or acrylic and have an almost dark blue purplish look. Then for the 1550 nanometer LIDARs, you have a different covering again, which can be specialised glass like a germanium or something, but in the end the main thing is that you can't just use optical glass. The other property of both LIDAR and radar that's important is they're one very specific frequency, effectively produced with the equivalent of a laser, even if they're spread out by a lensing system. Being one specific frequency, with a slight random variation between that used at different times, allows multiple cars to be all on the highway, sending out their pings like flashes of a flashbulb without all interfering with each other, being randomly allocated frequency and randomly allocating the time between pulses. This can allow for as many as 400 cars to be all cruising down the highway, sending out their little pings or flashes and not jam each other or interfere, so the whole system can still work. But all this is just how the sensors work. Yet what is more important is how the data from the sensors can then be used to build a view of the real world. How we build a world view, and what camera systems try to emulate, is turn data from visible light sensors into a model of the real world. Picture the room shown here. This is just an AI image, and there's no real room. But still, our brain turns the dots that our eyes detect in the cone sensors that are arranged as dots all around the eye into an image with not dots, but surfaces. And in fact, those surfaces are translated into objects. Everything we see when we look around is converted from the dots our eyes see by our brain into an object. That object has attributes. We see a table. We have characteristics. Can we lean on the table? All of these things we assume based on our knowledge of those objects. It has chairs. Can we sit on the chair? Can we pick up a chair? What would happen if we walked into a chair? All of those things come not from the image, but from the data in our brain that we reference just from the dots that our eyes detect. Even with just an image without any depth information, the worldview our brain creates includes depth. Our brain is only able to do this accurately because it recognises every object, enabling determining relative size and distance. This is only possible with images where there is an understanding of every object. And things like Escher drawings illustrate how there are some limitations. It's said that we only see, at any one time, an image about the size of our thumbnail held at arm's length. Yet we build up this complete worldview around us from the sensors in our eyes. Our eyes work with 3 wide colour bands. These colour bands overlap. There's not even clear red, green and blue that are separate. As you can see on the chart here, the red has actually 2 peaks on it at different frequencies, so that we can see the red and green combination as one colour, yet the red and blue as more extreme in high frequency than just blue by itself, or blue in combination with green, because we actually never see blue truly by itself. The key here is it's not just the raw data from the sensors, it's the ability of the computing systems to turn that raw data into a picture of the real world. That determines how well sensors can work in allowing artificial intelligence to build a view of the real world, for self-driving, for robots, or for anything else. And that's why all these sensors that we're building into robot cars and robot everything are becoming more and more relevant to what's going to shape the world in coming decades. Now, there's a philosophy we can rely entirely upon visible light, because the human mind relies almost entirely on visible light, and there's a whole lot of other sensors as listed here. But The most important in finding our way around for most of us is visible light, and we manage to do it quite well. So, can cars do that? Or could we have even better navigation by adding sensors that humans don't have, allowing to do things even better than humans do? So, how do these sensors build their picture of the real world? Starting with the most simplest, the ultrasonic sensors, which really only get one reading, how far away the nearest thing is. But there's a grid of ultrasonic sensors, or a line at the front and a line at the back of the car, enabling combining the data from different sensors. This means that you can do triangulation. If you see a signal in two sensors, then it could be between the two, or it could be two different objects. How do you work out which is which? One of the main ways to differentiate is to also use the fact that you have another sense, which is how far the car moves. So you can combine the movement of the car with a change in distance to the object. And then, by some geometric calculation of basically Pythagoras' theorem, you can calculate that the object must be at an angle, because if it was straight behind, for every centimetre closer, you'd get the object would become a centimetre closer. If it's at an angle, the steeper the angle, the smaller the change in the noticed distance will be, because a large amount of the distance becomes how far the object is to the side of the sensor instead of directly behind the sensor. So combining the fact that you have several sensors and some other data allows building a better picture of the world. It's not a great one, but it's enough to give an audible warning of close objects when parking. Now that same audible warning can feed into the system's computers that have other data to enable a total parking solution when driven by the car itself. But you're not really going to park a car just on those sensors, which is where we get into LIDAR, radar, and combine it with the data from cameras. Again, all ultrasonic LIDAR and radar send out clicks. LIDAR and radar are basically the same apart from the frequency. Now that frequency does make quite a difference to how much resolution you can get, what materials the clicks that are sent out can pass through, and how far you can get the clicks to run and detect the background. Detecting clicks always works on the basis that there can be that type of signal already present in the environment, but you expect a jump in the size of the signal in response to the click coming back. So that if there's sound at 40 kilohertz, you'll still hear a jump in the amount of 40 kilohertz following the click going out from the ultrasonic sensor. You'll also, even though the infrared is always present in the environment, a LIDAR will see a jump in the amount of that frequency directly corresponding to the reflection of the clicks. As with ultrasonic sensors, the idea is to build an image not just of one point, but of the complete environment. So how do you build an image that's much more like the one we get from our eye, where there's a whole lot of recorded points? The ultrasonic sensor for each individual sensor only give a single point reading. A single point reading for a LIDAR or a radar, well, you require a whole lot of LIDARs and radars to build up a world view. And if using LIDAR and radar, you're going to require a whole lot of LIDARs and radars to build up. Now that is actually done with both LIDAR and radar. Cars have an array of LIDARs around the car, and both LIDAR and radar systems sometimes send out a whole lot of beams all at once. They typically also use those beams sent out all at once to scan, which is the next technique. This scanning technique is where you move the beam. By moving the beam, you can have a very focused beam, very much like a laser beam used in a distance measurement sensor. Imagine a laser beam as used in a distance measurement sensor, like one I have here. Imagine pointing the dot of the distance measurement sensor at one point and then scanning or moving the sensor gradually across the scene in front of you. Then the next line, then the next line. Well, that approach is a scanning approach. It means the beam, because it's focused, can work at a very long distance and can build up an image of something a long distance away, but it's slow and it takes a long time to scan. The next step is to actually have several of those beams, so you're actually scanning more than once. Now this technique is the way the LIDARs that look like a fez hat on top of a car, or an emergency beacon that actually you can't see flashing, that's mounted on top of some self-driving cars. This scanning system of LIDAR does allow picking up things at a greater distance. The other approach is, instead of sending out one dot, send out a broader beam, cover a whole area at one time. Then you've got to analyse the data coming back in order to work out what's how far away, where is it in the image. This has two disadvantages. One is that the further away the object you hit, the weaker the beam will be because it's spreading out as it goes forward. The second problem is, in the data coming back, where did the actual reflection of the echo come from? Well, there are two ways of working that out. One, as used in simple speed radars, is to work out the angle that the data comes back at a given time. So a speed radar works on a couple of things. The echo of the click coming back will be changed in frequency with the Doppler effect, giving the speed. The second thing is, can actually measure the angle from which the reflected signal was received. Now, these simple radars only record one angular piece of data at a time, so if there are two cars travelling at identical speed coming towards it, it's difficult for it to determine. But if there are two cars travelling at identical speed, then both of them are either speeding or not speeding. If the cars are travelling at different speed, then you'll get two different signals at different frequencies, and you can work out which one is a speeding car. You can improve this by collecting multiple echoes that will result from reflections from different objects at different distances, recording angle, speed, and distance for each of different moving objects at different speeds and or distance. This does collect multiple points, and is also how most millimetre wave car radars work. But it's a very simplistic view of the world that recognises the speed and distance of objects in motion, but not what those objects are. To see more of the world and to collect data from the whole image requires a way to collect the data at a whole lot of points in an image. You need something like an image sensor that's used in a camera. Although only one type is used in self-driving, there are actually two types of time-of-flight sensors. There's avalanche photodiodes, or avalanche single photon diodes, which are used in direct time-of-flight sensors as used in self-driving. These have all the features described previously for flash LIDAR. And the second type is indirect time-of-flight sensors. These don't send pings and don't measure time delay directly. Instead, they use phase shift. They send the signal out continuously, which means they're much more subject to interference. They require much stronger lasers for any given distance, which typically means that once they're around consumers, the absolute maximum range possible is around 5 metres. These are the ones used in smartphones, all but the very high-end ones, which can actually use true time-of-flight. In cars, they're also used for in-car monitoring to see if the driver's in the driver's seat, if there are children or pets left in the car, and various other functions. They're used for robots and drones for near obstacle avoidance. And while the range that's safe around consumers is limited to usually around 4 metres, when used in areas where it's known there'll be no humans, you can extend their range to 10 metres in industrial applications, and in very advanced systems, they can reach even 100 metres. But, once again, they have to be nowhere near people. The other problem is reliability, since having multiple indirect time-of-flight LIDARs all in one area will effectively all jam each other. Now, you're going to be focusing frequencies that aren't visible light, which means you need very different lenses. And as explained on the chart on screen here, the different frequencies require different techniques to focus the returning beam onto an image sensor that senses the exact time the signal was received, rather than, as with visible light, record the intensity. Now, this recording of the time allows building up a 3D depth map. That depth map is very different than the imaging we do with our eyes, but it's yet another source of data that we combine with visible data to build that picture of the world. A key point here is that radar is not all radar and LIDAR is not all LIDAR. These systems used in military aircraft with scanning radars would send out multiple beams at once and give us those amazing pictures of UFOs that are still blurry due to the lower frequency of radar, but they actually give us a picture of a whole scene. not just the one dot that you get from a speed camera LiDAR. Not just the one dot that you get from a speed camera radar. Similarly, all LiDARs are nowhere near the same. You have those scanning LiDARs that spin on the roof, or what they call flash LiDAR, which send out a signal like a flash bulb going off that illuminates a whole area and detect the reflections coming back from that whole area on a sensor. And those LiDArs operate at two key main different frequencies, with one frequency closer to visible light, being higher resolution, but still being picked up by our eyes, so being restricted in intensity so it doesn't cause eye problems. The lower frequency can be sent further, goes through atmospheric conditions that can reduce the transmission of visible light, but is lower resolution. And the resolution of the LiDAR is another huge factor in what you can build up for the world. The bottom line is that none of these other sensors is a replacement for vision. We don't have the database to look up the objects and work out the objects, but we can get additional data. That additional data avoids optical illusions. Even the human brain, with all its training over its whole lifetime, can be fooled by something like an Escher drawing. Having this other data does enable us to not only perceive things we can't perceive with human senses, but also avoid potential for optical illusions, which could be very dangerous in a self-driving scenario. Now remember that the only thing that can see signs and the world as we create is visible light. LIDAR, radar, ultrasonic, they all send out one single exact frequency, which means they have weak spots of things that don't reflect well that exact frequency, but they also build up an image that's far more basic than even a monochrome black and white image, because that covers the whole span of visible light frequencies. These are just one specific frequency. You could create signs that where one part reflects that frequency and another part doesn't reflect that frequency, but these signs don't exist in the real world today. So a lot of the things that we need to pick up can still only be picked up by visible light. But we can provide a backup. Elon Musk has once said that backup can be a crutch, allowing too much reliance on the crutch and not enough ability to map those dots that we get from cameras into real-world objects. Do we need to know the real-world object if we just know its shape and how fast it is? Well, for a lot of things, we do need to know. That crutch mechanism is one of the differences between the experience of the first time you get in a car with radar cruise control and say, wow, this seems so close to self-driving. But the more you experience it, the more you realise there's situations you just can't cope with. The more complex the situation, the more data is relied upon and the bigger the world view is needed in order to handle that complex situation. And that's where these sensors come into play. A comparison of different systems and where things are at will be covered in a separate video.